Hello guys, I'm back again with another live stream. Today I'm thinking of revising uh, all the things that I have been doing so far. So revising in the sense not only like seeing and looking through it and passing by, but I will be like whatever we did, the whatever algorithms we solved. First, I'll be looking into every of the algorithm. I'll try to code it by myself, and then I'll compare whether it there is any problem in my code or not. If there will be, I'll try to rectify it and then move on. Next, what I'm thinking is after that I'll be picking some popular questions that are being asked in MNC's company. So like basic hard level question and then medium and then easy. So like those questions I'll be picking up and I'll try to solve. Uh, in solving, it might be possible that I might not solve the question because I already know the technique and everything, but algorithmic part I'm pretty much sure that I'll be coding it on my own so that I can like get a better understanding or better hands on it. So it'll be like if I get any type of question, I know that this is based on this algorithm. So it should not be like that I'm reminding myself that what the algorithm was, what to do. So algorithm should be on my mouth. Rest of the logical part I should be handling in separate. Okay, so so that is what I'm thinking today first, and after that if time allows, I'm thinking of giving the contest, virtual contest, which I didn't give to today. I should have given that, but I did not. So I'll be giving it virtually. So yeah, yesterday I was feeling really sick. My body was paining a lot and my head was also paining, so I did not stream yesterday, but I solved two hard level question even though I was feeling sick. So these this alien dictionary and minimum total distance traveled, this question was really good concept of DP. If you know 01 DP, it'll be understandable, but still you need to understand the logic behind it. So it's really good. This question is really good, I would say. Okay, so let's jump into. I've already created my repository for preparation. Of everything, I'll try to pick from here, and maybe I'll create a Google Docs. No, I need a Google Docs here. I'll let's pick any Google Doc. Try Docs for work. Uh, I need a simple Google Docs, man. Where is it? Yes. So I'll be writing those algorithms over here, probably. Meeting notes, email draft. Okay, there are lots of things that I can do over here. Fine. So I'll be writing my algorithms over here. I'll practice in the Google Docs because like what happens in like big MAANG companies. I'm not sure about the rest of the things, but Google does this. So if I have a practice hands-on on these things, I would preferably be comfortable with rest of the companies also. like Amazon, Microsoft, and Meta, Apple. So I'll be much more comfortable with rest of the things. So okay, let's dive into algorithmic part. So I will always, as always, I'll be doing 50 minutes of uh, Pomodoro, which is focus time, and after that I'll take a 10 minutes of short break, and in between I'll take a long break for my lunch. So yeah, so without wasting any further time, let's directly jump to preparation. Let's go. So first I'm thinking of picking up all the graph algorithms. So BFS, DFS. So maybe I'll directly go with BFS algorithm and DFS algorithm without watching it, because it's very obvious that these two things should be there in your mouth. Like whenever you want, you just have to write it down. You don't have to do anything. So okay. So let's try for BFS first. So I'm starting graph BFS. So probably I'll create a function which is a graph BFS part. So for BFS I'll be considering two things. I have n is like the number of nodes, and I have total number of edges, which will be given me in the form of vector. Most probably the format looks like this, and I need to now create a adjacency list. So I'll create a adjacency list for this, which will be size of n. Now what I will do, I'll iterate over this edges. Let's take it auto ampersand edgh of edges. So adjacency list of a edge edg edge of 0 0 dot pushback edge of 1. So this will basically create a edge from 0 to 1, and I'm considering this graph as a undirected graph, because directed graph will always have a direction. So but I want to handle the undirected part also at the same time, because if I'm able to handle undirected part, then I'll be very much comfortable with handling the what I would say directed one. So I have my adjacency list created. Now I need one more thing, which is my visited vector int visited, which will also be a size of n and initialized with 0. That means I haven't visited that node yet. So this is what the basic adjacency list and the visited will be. Now I need to create something which will help me in iterating. So graph breadth first search, it will it is actually a two type. First is starting from a single source node and then going to multiple nodes, or other BFS is starting from multiple source node and going to multiple directions. So multiple BFS and single BFS, we can try both. So currently we'll think of like keeping a single source BFS. Multi-source BFS is also like kind of same thing as single source BFS. That will, I think, can be handled in the and I would say Kahn's algorithm, when I'll try to solve the Kahn's algorithm. So for this BFS, we are only handling the BFS part. So for this we need Q, because we are not handling any edge weight or something like that, so we'll take Q. I'll push in this queue my source node. Let's suppose my source node is starting from 0. I'll mark this in my visited, that I have visited this. Now while my queue dot empty sorry, while my queue is not empty, I'll move uh, queue has a source node, so it will be like current node. Current node is nothing but queue dot front. Because this is queue, so we are pushing the first thing from front. If this would have been a priority queue, then it would have been queue dot top instead of front. So I have this queue dot front in my current node, and I'll pop this out. Now I know I have traveled this, so maybe I'll keep answer list that result, where I will push not queue result dot, this is a vector, so it will be pushback current node. So I push this current node. Now I'll be traveling its adjacency list and its neighbors, so it will be something child of this adj adjacency list of current node, right? So this is the child node. What I will do is I will take this child node, check whether if it is visited or not. If visited of child is equals to 0, that means this is not visited yet. So what I will do is I'll mark this child as visited, and also I'll push it in my queue dot push child. Correct, I've popped from my queue, so this queue will eventually ends, and at last I will return my result. So this is what my graph breadth first search looks like. Let's see if I'm missing anything. So we have this BFS, valid BFS. Let's check my valid BFS. जोर से बोलो bro, I'm already saying aloud. ब्रेकफास्ट नहीं हुआ, हो गया ऑलरेडी, ब्रेकफास्ट डन. जोर से बोलो जय माता दी. So this is my start node. I have visited of this, correct. I pushed in my result, I popped it, I went to its adjacent nodes, child nodes. This is my new node. I'll check it, I'll mark it, I'll push it. Are you missing life? Yes, bro. I think I am missing life. I think you are enjoying life out of your stream, right? You said that you will be streaming from November. From what I remember. So this is the node. This is the cost. This is the mask. So we have node as well as mask. Two thing in my visited. Yes, Feb. Bro, February is too long, bro. How am I supposed to wait till February for you to start doing live streams again? Your fans will be very much sad about this. So what in this word ladder we are doing is we are having a queue. I started with my begin word. If my begin word and is my end word, and result dot size is 0, I'll directly push it. If else if current dot size is equals to result dot size, then I'll push back. Feb is the shortest. I know that, but November, December, Jan is the longest. I think December and January has 31 days. So that's the longest days that you are not doing streaming. Okay, so this word ladder 2 is if you think I might try to explain it a little. So we have a begin word, we have been given a end word, we have a word list. So this word list will contain multiple words. So I need to start from begin word. I have to change a single character at once and check whether I'm able to reach this end word using this word list or not. So if I change a character in this begin word, it should be present in the new word should be present in the word list. If it is present, I will push it in my queue. If it is not, then I'll not push it. So for that I have created a vector of string. So for checking everything in my word list, I am doing what I am inserting everything in a map so that I can like access this in O of one time. I do not have to like access it more than O of one time. So for that I created a word map. Now I created a vector of string q. I'll push this begin word at start because I don't have any other word. Now what I will do, I'll try to change this word to different characters and check whether it is present in my word list or not. If it is present in my word list, I will push it in my queue, right? And after everything, I'll after everything I will erase it in it from my word map because I have already you consumed that, so I don't want me to go back to that word again. So if I started something, let me So this is my begin word A, B, C. I'll change each and every character and check whether it is present in my word list or not. If it is present, I'll push it in my queue. uh, all the words that are present from here, that can be found from this, will push it, and after that I'll remove this from my word list, because I don't want word map. I don't want this word from here. I can eventually go back to here, which I don't want. That will be a loop. So I'll just simply erase it from my word map. So here I'm original string. I'm going to each and every character. I'm starting from this is my current string. I'm starting from A to Z. I'm changing into current string. If it is present in my map, I'm currently pushing back, pushing into queue, and currently popping back. So until and unless everything completes, after that I'll remove this original string from my word map after this for loop, and at last we'll be returning a result. So this is word ladder 2. So BFS, I hope everything is perfect. Now let's go for depth first search. So DFS would be like not that difficult, I would say. So I have let's this graph DFS. So it will be having the same thing. Edges will get edges. So I'll create adjacency list, visited and result, and everything will be like same. So maybe I switch it. Let's switch it to the next page. So I created the DFS part. Now after this, what I will do, I'll do the DFS. Here I have this visited, I have a result. I'll start. From visited. Okay. Okay, let's do DFS. We have start node, which will be my 0, my adjacency ADJ adjacency list will go with me, and my visited will also go with me. So let's write this DFS. I'm not sure it will return what. Let's see if this is my start. My adjacency list will be somewhat this, passed by reference. My visited array will be also this, passed by a reference. So it'll be kind of if adjacency list of start dot size is equals to 0. I don't have anything here. I'll simply return. Else what I will do is I will be passing this result also, so that I can insert it in my result. I'll be accepting the same thing in here. Ampersand. And one more thing, if visited of start is equals to 1, I'll also, in this case also, I'll return. Else what I will do, I'll mark it as visited and then push it back, and the same thing for adjacency list. To ampersand child adjacency list of start. Like I should have given it a better name, like current node would have been much better. Return home. Yes, I will return home sooner, soonest. You stay at home. You don't go back to Pune. Hey bro, come on, like from other accounts now. I need likes. Share it in your WhatsApp status. So this is my new child. I'll check if this child visited of child is equals to 0. I haven't visited it yet. That means I can call this. So I'll mark this child as visited, and I'll do a DFS call with this child adjacency list visited result. So this is what my DFS would look like. Back to Pune on 13th road trip. Hey, why are you going back to Pune? Bro, you came just now. Don't go back. And why you came in the first place, huh? So, okay, let's do the detect cycle algorithms. We have lots of cycle algorithm for this. So we have bipartite graph, which I will do it. Directed graph, smallest cycle, undirected graph, and a two-edge technique. I don't know what this two-edge technique is. It's actually not a any algorithm, but it's something really important. I'll come to this after some time. And then minimum spanning tree, we have this Prim's algorithm, shortest path Dijkstra algorithm, and topological sort Kahn's algorithm. So there are lots of algorithm. Let's do it quickly. Let's go for bipartite. Start from start. कार लेके आए हैं, वापस भी लेके जाना है अब. Why bro, why you are taking your car back, and why you will go? Don't go, let your brother take his car and go back. So after that you'll not come from Pune, you'll stay at Pune. Is that what you're thinking? Okay, bipartite tight. Bipartite graph. So it's something which is uh, which bipartite graph helps. It helps in, bro, can't drive 1700 kilometers alone. Bro can't drive. Yes. So when you will be back from Pune after this trip? It helps in. Does it help in detecting cycle? Yes, it can help in detecting cycle. It helps in detecting cycle mostly if there is any odd cycle. It marks everything into two colors. Okay, you'll go on 13th and you'll be back on February, and you'll stay where till February? Into two colors. It marks everything into two colors. Let's suppose 0 for red and 1 for blue. So let's dive into the code for bipartite, whether it is a bipartite graph or not. So bi, P-A-R-A-T-I-T, it's kind of is bipartite. Let's say is bipartite. So in this also in this also will be given to few things. Bipartite, I'll be having the number of node, and as usual will be getting the edges list, and I'll do the same thing. I'll create the adjacency list. Let's shift it to the next page. Okay, so we have this adjacency list. Now there'll be a starting node. Maybe I can start from any of the node, because like if there is an odd cycle, it will detect it. If odd cycle, then it is not a bipartite graph. If there is no cycle, then it is a bipartite graph. If there is an even cycle, then also it's a bipartite graph. So it's the thing that we have. So we are checking like a kind of bipartite thing. So we will be having a visited array, vector int visited. Hey Saurav, you didn't reply me where you will stay till February. I asked that question. Of size n initialized with 0. I'm saying that if it is color 1, then red. If it is color 2, if my visited is 2, then it is blue, and if it is 0, that means unvisited. 0. If it is sorry, if it is 0, then unvisited, right? So I can start with any of the color to mark it. So maybe I'll do color as red initially. I'll push it I'll start with any of the node. So maybe I'll start with 0. So I need to create a queue of integer q, which will be 0, node 0, and visited of 0 will be marked as 1. So is it bipartite on like directed graph only? Check is by. This should not be a directed graph. This should be undirected graph. Yes, there is no direction to the graph. So let's initialize with -1. For red, it's for oh my god. For blue, it's 0, unvisited -1. I'm starting with let's suppose color red. So I marked this. I'm starting with color blue. I marked it with color blue. What I'll do, I'll try to visit its while. So this will start while my not q dot empty, until and unless my q is not pty is not empty. What I will do is I'll take the current node. Current node will be q dot front. I'll take the current color, which is visited of current node. This is the color. Now I'll try to explore its child. So the new color that we will be adding to this current color is current color XOR of 1, which will switch between 0 and 1, 0 and 1, something like that. So even I don't need this color, right? Okay. This new color, let's try to visit its adjacent node, and while visiting its adjacent node, I'll check whether it is painted or not. And if it is painted, so if my current color matches with the visited color, if they are same color, then there is an odd cycle. So it will be kind of that. So let's visit its adjacent. Child node, I'll be adjacency list of current node. So I'll check if there will be like either it is not visited or it is visited. So if it is visited, what color it is, I'll have to check that part. So if suppose if visited of child node is not equals to -1, that means that node is already visited. So if that child node color is same as my current node color, so and if visited of child node color is same as my current color, if child node color is same as my current node color, then means there is a odd cycle. So I'll return false over here. Else if I'll only push it in my queue when it is equals to -1. Sorry, AISIDD. So if it is not visited, I'll make it of new color and push it into queue. Queue dot push I think this child node will be pushed over here, and visited of new child node is equals to new color. And also after pushing q dot pop, I need to do q dot pop else, and at last I'll return true. So this is my bipartite graph. Let's check if color of new node is same as current node color, then we'll return false. If it is not visited, then I'll push and mark it as new color. Perfect. So bipartite is also done. What's next? So I need to detect cycle in directed graph. So I'll try for creating it for undirected graph, because directed graph is just what I would say a constrained version of undirected graph. So if we know how to detect cycle in an undirected graph, I would be like very much comfortable with detecting a cycle in directed graph. So let's code that out. Let's go to the next page. Detect cycle in undirected graph. GRAPH. Yes, correct. So detect cycle in undirected graph. Okay, so what it will be like detect CYCLE. Detect cycle detection is kind of a two-way part. One DFS, I can use DFS for doing the cycle detection part. I can use BFS for also doing the cycle detection part. So both of them is correct. So right now I'm doing a DFS solution for this, detect cycle in undirected graph using DFS, and BFS is also like will not be that much difficult. Okay, so let's try it. So it's the same thing will be given, like uh, number of nodes, vector int edges. I'll create the graph for this. I have already code. I don't want to repeat the same thing again. So I'll go through this edges and pick each edge, add it to my adjacency list. So I have created my adjacency list. I will be having visited of size n marked as -1. So I'll start over this. So I'll check if visited of I is equals to -1, that I haven't visited it. Now I need to check whether there is a cycle with starting with as a this node or not. So if is cycle, we are getting true, so we'll return true over here. That means there is a cycle, and if it is not, I'll return false, that there is no cycle corresponds to this. So is cycle will start from this node, will get this adjacency list. Let's code this. Is cycle will return boolean. We have current node, we have this adjacency list. Let's take this adjacency list. One more thing, that I need to pass my visited array also, and I need to accept this visited array over here, which will also be passed by reference. Okay, now if visited of current node, visited of current node is equals to kind of 2 already completed, I'll return that there was no cycle. Now if visited of current node is equals to if it was in already visiting state, I need to return true, that okay, I got this a cycle. I need to have a parent also, current node and parent, because when I'm checking for undirected graph, I do not want to go back to that node from where I just came. So it's parent, I do not want to go to its parent back again. Okay, so I'll handle that part. I'll mark this current node as I am currently in a visiting state for this node. I'll iterate over its child. Okay, ampersand child adjacency list of current node. There's one thing that I need to check. If the child node is not equals to parent, so I have to have this parent also over here. So if child node is not equals to parent, what I would say that okay, then I can check, then I can go to that node, and if that node returns anything like is cycle in I'll pass this child, parent will be my current node now, that I do not want to go to this parent again. Adjacency list and my visited. Now if it returns true, I'll return true that there is a cycle. I do not have to call anything again, and if it returns false, I'll go calling. So after this I'll mark this visitd visited of current node as 2, that I have completed visiting, and I'll return false from here, that I did not detect any cycle yet. Okay. Let's see. And if it would have been a directed graph, then I don't need this parent and child relation. So there should have been no parent. Directly I'll call this method instead of this if condition. So if was a directed graph, I would have directly called this method instead of this parent child. I would have never passed this parent. So let's see. Detect undirected graph. This is new node is not equal to parent. I'll call this to this. Perfect. Looks fine to me. Detect cycle in undirected graph using DFS. So BFS will be something like, I started with a node. I'll traverse all its neighboring nodes at once. So there will be a node which would have been already visited from some other path, and from some other path we are again visiting that node. So if I'm visiting that node, that means there is a cycle. So BFS would be like pretty much easy or very much intuitive. How I'm guessing it. So I think I should if I'll skip that part also for BFS, it'll be not that difficult. If you want, let me know in the chat. I'll do the BFS part also for detecting cycle in undirected graph. The only thing that I need to make sure in BFS also, that this parent child relation, I do not visit from a node, I do not visit back to its parent, because that will obviously going to give me a wrong wrong cycle. Even there is no cycle, but still we will get a cycle. So that thing we need to keep in our mind. Rest of the thing is okay. So detecting cycle is done, I think, for directed graph and undirected graph. Smallest cycle. Okay, there is something called smallest cycle. See, in this case also we can find the smallest cycle. If we return some value, we will be able to detect the smaller cycle. So this DFS part also will give me what this smallest cycle is, we can solve this using two edge technique. Two edge technique is something, I'll explain. Two edge technique is what I have will be given edges, right? So this is my edges list. I will not be creating any graph with this edges list. So we have this edges list. Suppose we have from 0 to 1. Come on, okay. We have a graph like 0, 1, 2, 3 and back. So 0 to 1, 1 to 2, we have 2 to 3 and 3 to 0. So there will be like many cycle possible with this two edge technique. Suppose this is a cycle. So what I will do, I will not create this graph. This is the adjacency list that we are talking about. So we will not create the adjacency list for this. What basically we'll do, we'll create the eventually we will create the adjacency list, but on the go. So what I will say that, okay, I have this edge as 0 and 1. Now without connecting this edge, check whether if I'm able to reach from 1 to 0. Is it possible to any way to reach from 0 to 1 or 1 to 0? So this is what. So currently my adjacency list will be empty. So adjacency list will be like empty, nothing will be there. So from 1 to 0 I cannot reach. So what I will do is I'll write 0 to 1 and from 1 to 0 I'll add this in my adjacency list. Now I'll go from I'll take another edge. I'll take edge 1 and 2. Now I'll check, is it possible? I haven't created a edge connected in my adjacency list. Is it possible to start from 2 and reach 1? I see 2 is not there. So no, it's not possible to start from 2 and reach to 1. So I'll add 2 to 1 and 1 to 2. Now I'll start with, so till now what is how our graph is looking like 0 to 1 and 1 to 2. This is our adjacency list, how it is looking. Now I'll start with 2 to 3. I'll check, is it possible to start from 2 to 3, start from 3 and reach 2? No, it's not possible because 3 is not there. So I'll add it 3 to 2 and 2 to 3. Now 3 to 0. Now we'll check. We have this graph like this. Now we'll check, is it possible to start from 0 and reach 3? We can say yes, it is possible to start from 0 and reach 3. Then I could say that yes, this cycle is possible. And whatever the length of the cycle will be my shortest length, smallest cycle. So this is what I am doing here. So I'm creating a BFS with A and B. So I'm checking whether from B can I go to A. This is my adjacency list. This is my visited array. So obviously I'll start with start and 0. I have this queue. This is node. This is length. If node is equals to and return length. Yes, if we are able to reach from start to end, I have this start in my queue. If we are able to reach from start and else will iterate over its neighbors and will mark it. So this is how we will be solving this smallest cycle. So detecting cycle, BFS, DFS is done. The next is a minimum spanning tree, which I'll be solving. Then Dijkstra algorithm, and then Kahn's algorithm. So this will summarize my graph part, and then I can go for searching algorithm, KMP algorithm. This is what KMP algorithm is. It's good algorithm. Okay, so I'll be taking a 10 minutes of break, and after a break, we'll come again. We'll start from minimum spanning tree to Dijkstra to Kahn's algorithm. So I'll be back in 10 minutes. Don't go anywhere. See you. Okay, I am back. Let's go. So we did something like that. Next is Prim's algorithm. I'm thinking of doing the Bellman-Ford algorithm also for like Dijkstra algorithm, the shortest path algorithm. So after doing Dijkstra algorithm, I would pick uh, one Bellman-Ford algorithm or Floyd-Warshall. I guess the both are same. Any one of them would work. So okay. So first, before that, it's the Prim's algorithm for minimum spanning tree. That's nice. Minimum spanning tree, which is going to be my Prim's algorithm. Okay, so for Prim's algorithm, what Prim like minimum spanning tree states that what is the minimum cost to connect all the nodes. Like you can remove most of the edges, but whatever the edges left should have some minimum cost. Should be minimum and should be sufficient enough to visit every other node. So I can even start from any of the node. It doesn't matter from which node I'm starting. For minimum spanning tree, what are the things that are required? So I would say like mm, the start node. I need the start node, and then from that start node I need uh, what is the total number of nodes that we have encountered yet. Okay, and what is the cost? So cost will be like uh, at start, and then the current node where I am, and what is the length till now. So if length reaches the total number of nodes, then I will return the cost, minimum cost. So these are the three things that I'm thinking of keeping in a minimum spanning tree for Prim's algorithm. And obviously I'm going to use the priority queue for that wait node and parent node. Yes, there was one thing that I need to know. There might be two paths possible to reach. It's something from 1 I can reach 3. From node 2 also I can reach 3. Might be connected with something like 0, node 0. From 0 I reached 1, I reached 2 suppose. So this is cost of 1, this is cost of 3, this is costing 8. So from 0 to 1 I reached, so the 0 1 edge will come first, and from 1 to 3, from 1 to 3 I've already uh, Okay, and this cost was like 3. So from 1 to 3 I visited this, but I will not mark this as visited because I can even reach from 2 to 3, which will cost me eventually less, 5 costing, and this will cost me 9, a total of 9. So for Prim's algorithm, if we need edges also, for that I need to keep parent. There's one thing that I need to know. If okay, where I went, the visited part. I'll not go to that visited part again, right? So visited part will stop us from making any recursive call. So okay, minimum spanning tree will get the total number of nodes. We'll be having vector and ampersand edges. So from this I'll start creating a graph. First I need that adjacency list, and visited array. So I'll create a priority queue because age weights are different here this time. So priority queue will be the one helping me, and I need the smaller one at the top. For that I'll be creating a priority queue, and in my priority queue I'll push 3 things. First, the weight, initial weight, the source node and its parent. So 3 things that I'm pushing is the weight, source node, or maybe I would say current node, and its parent. Right, and in my visited I'll mark this node as visited. So while not q dot empty, I'll take out all the three things. First one is like weight, so pq dot top of 0 will be my weight. The second thing is my current node, which is nothing but pq dot top of 1. The third thing is my maybe current parent, which is pq dot top of second. Okay, now if current parent is not equals to -1, that means this edge is, I need to push it in my resultant. So it will be like current parent comma current node, and total weight will be added. So I need to have two things here, which is like current no, I need vector int resultant, which will store the edges and total weight, which will be initially 0. So okay, every edges will have three things, like from here to here I'm going, this is the weight for going from here to next node. So it'll be like not directly, it'll be pair of integer where edges of 1 will tell me, and edges edges of 2, edge of 2. So this is the same thing which I want from there to back to this node. Okay, and also I'll pop it pq dot pop. Okay, this is should be also pq. It's pq, right? Okay. Now I'll mark this as visited of current node as 1, that I have visited this current node. I'll go to this child for auto 1% child from adjacency list of okay. So we have this child. I just need to push it. I need to check if this is unvisited. I'll simply visit this child, so I'll push it in my queue. Okay, this child dot first. Maybe I'll make something like this. new node is equals to child of 0 int new weight is equals to child of 1 and visited of new node if it is 0. I'll add this current weight. No, not current weight. I'll add directly new weight because I'm adding it in total weight eventually. So this new weight, new node as well as current node will be its parent now. Return result or total weight, anything would be fine. Marked it as visited, new node, new weight directly, new node. So do not mark the neighbor nodes in the visited array. This is something I need to remember, right? Okay. So this is what our Prim's algorithm is. Now let's go to Dijkstra algorithm. The Dijkstra algorithm. I don't know. Dijkstra algorithm is like is the shortest path algorithm visiting from a source node to every other node. So for this I need a like a visited array as well as like the weight. Okay, so I need to have this Dijkstra algorithm. Let's code this Dijkstra algorithm. So it will return something integer. Dijkstra algo. It will take same two things, integer n and vector int, not vector int but pair of int comma int. No, it'll take vector int. Edges, I'll create my adjacency list. And my visited array. So there is some change in my visited array because I need to find all the nodes. So it will be something int max. Every node visited is int max because I haven't visited it. The only visited the only node which will not be int max is the current node from where I'm starting. So okay, so let's start. Let's create a priority queue. priority priority queue, which is nothing but this will have, I need the smallest one at the top, so I'll be creating a min heap kind of thing, and I'll push it in my queue. First wait, and maybe like a starting node is also 0. So there are two things that I am keeping in my priority queue is like wait, and then the current node kind of thing. And also visited of 0 will be marked as 0, like, because the cost of visiting this node is 0, because from here we are starting. So while not pq dot empty, okay, so it will be something like very much similar to Prem's algorithm, where we will not mark it visited when we are okay, we are not marking it visited, we are just changing its cost, right? So I'll take the current node out from my priority queue. No. Okay. And pq.pop, my priority queue's work is finished. Now if there is something related to it, if visited of current node, if this weight is greater than the weight that we have, so what we will do, we'll update this visited current node with the weight, new weight, else I might like continue from here, because if the visited of current node is already smaller than the weight that we have, why we will be like dealing with this node? I already have a path which has weight lesser than this, and that path will go further. I don't need this to continue with me. Now I'll like iterate over its adjacent child, adjacency list of current node, okay, saint new node will be like child of 0, and new node weight will be child of 1. Now if visited of this new node means weight is lesser than is like greater than current weight, we have weight plus new node Wait, if that is the case, what I will do is like visited of new node will be updated with wait plus new node wait, and in my priority queue I'll push wait plus new node wait comma new node, and at last I can simply return the visited, which will tell me that what's the cost. So let us see. Dijkstra algorithm, we have this node and the distance is 0 and node is this. Some I'm iterating over its edge weight from adjacency list. Distance plus weight is if lesser than shortest path adjust, then pq dot push and this, and at last I'll return. So this will also work. I don't think that we need this, but if even if it is there, I don't think that Dijkstra algorithm will fail, because this is the only thing that I'm checking. If the current node weight is like greater than lesser than the weight that we are getting, will actually continue, else will update it and will go. Okay, just a second. There is something problem. If visited of current node weight is greater than the weight that we currently have, and if it is equals to the weight that we currently have, then also it will continue. Why I'm continuing? It might be possible there is other nodes also from here which will be costing lesser. If this is condition, update it, else not else don't continue, like let it go. Even if it continues, because adjacency list we are checking it here, so it will obviously it will stop. So this will be a dot first and this will be dot second. Even if we do continue, then also I don't think there is a problem, because uh, we have a shorter path which already visited that node, and we are coming from a longer path, and if weight is like greater, I would obviously after reaching that node I don't want to go any further. So like continuing is also I don't think is will create an issue here. Okay, so we have this Dijkstra algorithm also, Done. Let's do the Kahn's algorithm for the topological sort, and I would go for uh, Bellman-Ford algorithm after this. So let's do the Kahn's algorithm. So what is actually Kahn's algorithm? Uh, Kahn's algorithm, basically it helps in detecting cycle. Kahn's algorithm will help me detect a topological sort. Okay. Is there anything else beneficial in Kahn's algorithm? So for topological sort, we have two things. Like we have a DFS, which is kind of easier one, and this Kahn's algorithm. See, if we are doing a DFS for topological sort, that will also help me in detecting cycle. DFS for topology, doing DFS in topological sort is not that hard, but it requires some extra space also, stack space. The DFS is creating its own stack space, and we need a separate stack for creating it. But for Kahn's algorithm, even though Kahn's algorithm does the same thing, it will create a stack space also. Okay, let's try the Kahn's algorithm. So topological sort. So in this we'll have node or vector int, just I need to create adjacency list for this. And here I am not working with cost, so I don't need this pair. I need only a simple adjacency list. Right, as well as I need one more thing. See, so this topological sort will always be in DAG. Topological sort, topological sort will only work in DAG, which is like directed acyclic graph. It will not work in any other thing. So for that we need to have a directed acyclic graph. So I don't need an edge which has no direction. If that is the case, then like topological sort is not possible. If there is a cycle, then also topological sort is not possible. So Kahn's algorithm can detect both of the things, if there is a cycle or not. If there is a cycle, we'll say that DAG is not possible, topological sort is not possible. If there is no cycle, then we can say like, okay, it's possible. So as now we will be needing one more thing, which is the in degree, which will be of size n, initialized with 0. So in degree of edge of like 1, I'll increase, because from here I'm creating an edge to there, so that's in h1 in degree will increase. Now I'll create a q and I'll iterate over this in degree array, or I would say like n, and I'll check if in degree of I is equals to 0, then I would say that this is a possible like preferable start for me. So q dot push I, this is my start. And now while not q dot empty, I'll take this current node is equals to q dot front, because we are dealing with q, so q dot pop. Now I'll try to go to its adjacent node, so I'll have this child, its child adjacency list of current node. So we have this new child available with me. What I will do for this with this new child, I'll reduce the in degree of this child. If in degree of this child comes out to be 0, that means we can push it in my queue. So q dot push this child. And one more thing, for detecting cycle, I would say I'll increase this count node. Now I also need the topological sort for this. For that I need a vector int a kind of a result. So result dot pushback current node, and count node will increase. So at last, if I'll check if count node is not equals to a edges dot size, the total number of edges, then I'll say that okay, there is a cycle present. Else if they both are same, will return like result there is no cycle, and we can find the topological sort. So this is what Kahn's algorithm is. Let's check if everything is correct or not for Kahn's algorithm. We have q, we push back this node, we go to its adjacent, we reduce the in degree. If it is 0, we'll push it in my queue. And I haven't handled the like this part, count node part. Should I commit it here? So if instead of count node I can say like result dot size, which will obviously is not equals to my edges. Then I would say cycle present, and it's fine. Commit changes, commit directly to the main branch. Fine. So this is what Khan's algorithm is. So we are like mostly done with the graph part. The only thing that we need to learn now is Bellman-Ford, because I'm skipping that. I skipped that Bellman-Ford, but I don't think Bellman-Ford is that hard. I already know the concept, so I just need to like go through the Bellman-Ford algorithm once. Let's see. If the graph contains a negative cycle, then return an array consisting of only negative one. So it's same as Dijkstra algorithm, but this handles the so directed and connected graph. We find the shortest distance of all the vertices from the source node. It's the same as Dijkstra algorithm, but it can handle the negative. But if there is a negative cycle, negative edge weight, if it is there, then it is fine. Then Bellman-Ford can handle. But if there is a negative cycle, edge cycle, then I don't think there is any algorithm present till now. Or kind of like it's not. I haven't read it yet. So Bellman-Ford and Floyd-Warshall, they both are not handling that part correctly. Okay. Okay. So let's see my Bellman-Ford algorithm. So what do we have here? So we have this edges of 0, 3 to 6, 5 3 1 0 1 5 1. Okay. It's like from this node I need to reach that node, but I'm going via some other node. So what if it is possible to reach from this source node to target node that I selected? What is the minimum cost? Is it possible to minimize the cost directly, or if we go via somewhere, that will minimize our cost? So this is what the logic here is. Okay, so let's understand it. Okay, just a minute. Okay, so obviously we have the distance. I need to understand this. What is this edges that he created? Everything is a size of 3. Why? Like 3 to 6. Why we have from 0 we have something like this. Okay, okay. It's u, v and weight. Like from here to here, what is the cost? From here to here, what is the cost? From 3 to 4, weight is 1. From 2 to 3, weight is 1. Okay. This is my source node from where I will start. This is my edge list, and this is what v is what. Okay, total number of node. How many vertices we have? So we created a distance array of total number of vertices. Source node will be like 0, obviously. Okay. We are iterating this edges v times. We are taking the source node, we are taking the target node, and we are taking the weight. Now I'm checking if source node distance is not equals to I8 and source node plus weight is lesser than what we have in the distance. So I'll update that distance. Okay, that is fine. We are not even creating a graph. We are only handling it with this edges. Like this is the graph that we have, going from this node to this node. A little bit of confusing. Maybe I'll check somewhere else. Let's check somewhere else. So we have this graph, everything is initialized with infinity. This is my source node. So start relaxing edges during first relaxation. Current distance of B is greater than distance of a plus weight of a to b, that is infinity is greater than 0 plus 5. So we're directly checking in our map. So if going from here to here, so current distance of b is greater than, if reaching here is greater than distance of a plus weight from a to b, that is infinity is greater than 0 plus 5, therefore distance of b is updated with 5. So this is the first uh, relaxation that we are doing. During the second relaxation, distance of d is greater than b plus weight of b to d. That is infinity greater than 5 plus 2. So we updated with 7. So we started from b to d. Like b to d 5 plus 2, b to c 5, 1 plus s this. So from d to f, and c to e. Okay, we like I am understanding the concept is like very much similar to the Dijkstra algorithm, but the implementation part is little different, right? So I need to know like what exactly we are doing in the implementation part. This though I'd say it's fine. Since we observer changes in that. Hence we can say that there is presence of negative cycle. Okay, just it's also guaranteed to find the shortest path in graph similar to Dijkstra algorithm. Although Bellman-Ford is slower than Dijkstra algorithm, it is capable of handling graph with negative edge weights, which makes it more versatile. The shortest path cannot be found if there exists a negative cycle in the graph. If we continue to go around a negative cycle in infinite number of times, then the cost of the path will continue to decrease, even uh, though the length of the path is increasing. As a result, Bellman-Ford is also capable of detecting negative cycle, which is an important feature. So it will detect negative edge cycle and negative edge weights also. So if there is some negative edge cycle that we found, starts with a single source and calculate the distance to each node. The distance is initially unknown and assumed to be infinite, but as time goes on, the algorithm relaxes those paths by identifying a fewer shorter path. Hence, it is said that Bellman-Ford is based on principle of relaxation. Why relaxing edges and minus 1 times gives us a single source shortest path. Fine. Okay. Why this is so long? Okay, I understood the concept, but I need to check how we are handling the source, destination, and weight in the Bellman food. I might watch a video for this, but after a short break, and after that we'll start with KMP algorithm, our searching algorithm, which is way more important. So don't go anywhere. KMP algorithm is really important. We need to know this, and then we can go for dynamic programming question, and then we will revise, do the revision. And there is something binary search twist that I'll tell you. There is some trick. These two questions were like having those two tricks with the binary search. I would say I will work with that also. Okay, so I'll take a 10 minutes of break, then we will go for short test path, Bellman Ford algorithm, and then search algorithm, and then DP. And then we'll revise these questions again. And then we'll go back to like uh, Google questions and solve it. Okay, so I'll be back in 10 minutes. Don't go anywhere. See you soon. Okay, I am back. Okay, so we were reading this Bellman Ford algorithm. Relax all the edges. V minus one. Okay. Give me 2 minutes. I'm getting a call. I'll be back. I'm back. I'm back. I'm back. I'm sorry. कॉल आ गया था. I got a call. Let's see Bellman Ford's algorithm video. एक ही तो algorithm है. Bellman Ford. Okay. Okay. So this is something good. Good. Bellman Ford algorithm for like n-1 relaxation. Let's let's write code for this. Maybe I'll write it in Sublime, and I'll push it in my GitHub repository. Now actually I know the logic how we are doing this, so okay. We have this in graph, shortest path, save. So this we have Bellman Ford algorithm. We have n total number of node. We'll be having edges, which is currently like we'll have three things: u, v, and the value. And we have a start node. Okay. So edges is in the form of u, v, and w, where u is source, comma, v is destination, and w is equals to wait. Now we need to do the iteration a total of n-1 times, and then the shortest array will give me the result. If to detect negative cycle, what we can do is we'll do one more times relaxation, and if the value changes, then we can say that yes, we have that yes, come on, yes, we have a negative edgh cycle. Okay, so let's start our relaxation. So relaxation will be something. I'll start my for loop. I need to do n-1 time. So if there are 4, then my loop will run only 3 times. Correct. So n minus 1 time relaxation also will be having a vector int of shortest distance of size and everything initialized to maybe int max, the maximum value, and shortest distance of start is will be equal to 0. Now I'll iterate over all the edges. Iterate all the edges and relax everything. So for int, like I'll do the edg edge edgs edges. I'll take u as edg edge of 0. I'll take v as edge of 1. I'll take w as kind of weight. So if it's like from here to go there, so I need to know, like, if shortest distance of u is not equals to int max, then only I'll go, else it will go beyond, and which I do not want. So if shortest distance of u plus current weight is lesser than my shortest distance of v, if that is the case, so I'll update my shortest distance of v with shortest distance of u plus my weight, and this will be done in n time. If we want to check for cycle, we will do one more iteration, and if we find that shortest distance array changes, then we can say that we have detected a cycle. Negative edge cycle. Okay, so what we'll do this iteration once more, and if this happens, if any of this happens, we can say that there is an negative edge cycle, and if nothing changes, return shortest distance. So this is what it will be. Let me create a vector int of edges, which will be like 1 to, like 0 to 1 with a value of -1, or then 0 to 0 to 2 with a value of 5, 1 to 3 with a value of 2, 2 to 4, 2 to 4 with a value of -2, something like that. And then we can call this Bellman food algorithm, which will return me kind of vector of integer. Print it and I'll return an empty. That I'm not able to find it. I don't need this. I'll simply call this algorithm with a total edge of, suppose, like we have 1 2 3 4 4 edges. Total this, and source node will be 0. So this is my Bellman food algorithm. Nice. Let me push it to my GitHub repo. Where is it? Where is it? Where is it? Git add space. I have a mock interview. Okay. Git commit -m. This is something Bellman food and Google mock interview. Git okay. I need to pull origin main. That was just a small change. Minor change. Okay. Git push. Okay. Done. So I think no. If I refresh it, hopefully I'll get it. So binary search twist is fine. Graph, we'll have the shortest path. We'll have this Bellman food algorithm. Great. So we learned something new. We learned topological sort. Now we can go for search algorithms. And the first one is KMP algorithm. Let me copy this to whole thing, untitled document. Bellman food algorithm. Okay, this is fine. Now let's go to KMP algorithm. Like from here we are starting our search algorithms, where my first search algorithm is KMP algorithm. So this KMP algorithm is kind of an algorithm which helps us to find a substring in a string in a time complexity of big O of n plus m space complexity. It will take big O of n, big O of like n, fine. And rest of the algorithms, like except KMP algorithm, we have one more algorithm which is like we do it like hashing or something. I don't remember the exact name, but it's kind of a rolling hash type of algorithm that we do. But majorly a KMP algorithm is something which is mainly what we use most of the time. So KMP algorithm, see, it's the question is like we have a string str which is a b c d e f g h a b c d e f g, something like that, and we have another string kind of needle, we say a b c f. We need to search a b c f inside this whole string. So for this we have haystack. This is what we call haystack and needle. We need to search this needle in this haystack. So KMP algorithm does a very similar job. So KMP algorithm will be like kind of working over the needle. We'll need to create some prefix. Need to create some kind of prefix array which will help us to find the needle easily and also in less time complexity. So let's start our KMP algorithm. So we'll be having two string which is a stack and another string which is needle. So we will be creating a kind of pre uh, what I would say presum or prefix array of size needle dot size initialized with 0. We'll have two variables a and previous, both will be initialized from 0. Now while I is lesser than my needle dot size, this is something that I'm creating a prefix. So now if needle of I would start this from, instead of 0 I'll start it from 1. So if needle of I is equals to needle of previous, so prefix of I will be updated with previous plus 1 and my previous will increase if the needle matches. If they do not match, I'll have a separate condition for that. In this I'll check if previous is equals to 0. If previous went to 0, I'll simply increase my I. Else if my previous is not 0, what I will do is like previous is equals to prefix of previous minus 1. It will go back. If previous comes to 0, it will be previous will stay as it is. It will not change. Only my I will increase. If not, it will go, and in this case also I will increase, right? And it's like, okay, if I am increasing I'll simply continue from here. If not, I'll update it. I'll bring this. If they are matching, I'll move my previous, because in every case my I will be in an increasing. If they matched, my previous will increase, my I will always increase. If they do not, if my previous I will increase and I'll continue. If my previous is not equals to 0, I'll move my previous is equals to previous of previous minus 1, prefix of previous minus 1. This is how we will create a prefix array. And after creating this prefix array, I need to find it in my haystack. It will be like very much similar. Now I'll be like doing the searching part here. So searching part will be like very much similar. My I will start from 0. I have this previous, right? My j will start from 0, while I is lesser than haystack dot size. I'll run this. If my haystack of I matches with needle of j, I'll do what? I'll do I plus plus will obviously be there. My j will also increase with I. If they do not match, I'll check. If j is equals to 0, I'll simply do what? I'll simply increase my I and I will continue. If j is not equals to 0, so what I will do is like prefix of so j will be updated with prefix of j minus 1. Now in any moment, if j reaches needle dot size, that means we found the substring. Will return will return true, that we found. Else will return false, that we were not able to find it. Okay, let's check. So I have started my I. This is my prefix, size of m, which is my needle. If needle of I matches with needle of previous, which is here, needle of I matches with needle of previous, we are updating previous of I is equals to, oh shit, I did not update it. Oh, I did update it. Correct. Prefix of I is equals to previous plus 1. I increased my previous, and obviously we are increasing I. So this is also fine. If previous is 0, it's like obviously I'm updating it with 0 only, so it will be 0, it will not be anything else. Else previous is equals to previous is equals to prefix of this. My I, okay, here is something that I need to know. My I will, but when we are going back, will not update our I, correct, because we will compare the same value again. I forgot about this, right? We'll increase our I in this case. Even prefix of I is equals to 0 will not change anything. This will be updated to 0, but I'll increase my I. But here I will not increase my I. Why I will not increase my I? Because I'm moving previously. Maybe I'll compare these two values and these two value matches, right? Correct. I missed it. So in not in every case will be increasing. Okay, now my haystack pointer and my needle pointer are this. Until unless my haystack reaches to end, I'll check haystack of haystack pointer is equals to needle of needle pointer, which is nothing but I and j. If if they both are same, both will be increased. If they both are same, I will increase, j will increase. If they are not same, so I'll only increase my I if j is 0, else my like needle pointer will go back to needle pointer minus 1, prefix of needle pointer minus 1. And in any place if my needle pointer reaches m, which is nothing but needle dot size, my j reaches to needle dot size, I'll return true. Return haystack pointer minus m. Okay, what's the position? It's returning the position, so haystack minus m. This is the position that we found it. If someone says like find all the positions, uh, so I'll run this instead of returning it from here. I'll push it in my result and then I'll again go. I'll again run until unless I reach my n. It will find. It will start keep on finding that array again and again. But if my needle pointer reaches m, that means this will fail. This will throw some kind of like exception that there is no size of needle left. So I need to like go back one position, needle pointer minus 1. So this is some kind of KMP algorithm that we are using. It's like what if we found it? Total number of occurrences of a string. So it will be like to total number of positions where substring is present in string. No. Find all the position of substring in a string. C++. Find all position of a substring. String find. No. Print all occurrences of a string as a substring. So geeks is present at 0, geeks is present at 8. So okay, yeah, this is the naive approach. Well, I start approach to using inbuilt STL. This is index of S of, and from this position using two pointers, time complexity of n into m. So 0 and 3. This is what we want. This is my like pattern I created. Construct LPS longest prefix sum search method is where is search method will construct LPS. After constructing LPS will iterate if j correct, I will move one step back of LPS j minus 1. If they match, if I reach, I'll move one step back again if there is a match. If there is no match, I'll do the same thing again. This will find me all the positions. Yes, this is what I was thinking also, and this is correct. Fine. So all the occurrences will be like okay, where is it? If everything is true, like result dot pushback I minus needle dot size, and j is equals to, come on, j is equals to prefix of j minus 1. It will go back. Else I'll return an empty braces that we did not find. So we need to create a result vector int result, which will be n. So So this is my KMP algorithm. We learned Bellman Ford, we learned KMP algorithm. Great. So next, what we are going on. So we know the searching algorithm. These two questions are based on the same thing. Longest happy prefix and shortest palindrome is like same based on KMP algorithms. Then I think I should start with dynamic programming. Dynamic programming, like question recursive. If you know recursion, if you know memoization, it will be like uh, easy for you to understand dynamic programming. It's not that difficult. Uh, and we have this Google mock interview dog. If you want to look at it, view raw. Oh, okay. I'll download. This is a good mock interview doc. If you want, you can check this out. It has two questions. The first one is like kind of easier side, uh, kind of easier, a little upper of easier, but kind of easier. And then the rest, the second one is like upper medium, or I would say hard part. So you can attempt that also. And then we'll go for binary search twist. I'll explain you what binary search twist is. And then we are mostly we will be finished with the algorithms, and then will be revising the questions whatever we have. So let's take a 10 minutes of break, and after 10 minutes break we'll be back again. Don't go anywhere. We'll start solving more questions. So see you in 10 minutes. Bye bye. Okay, I am back. So, where were we? Okay, we completed graph. Let's go for binary search twist. I would say binary search question. So, what's actually the twist is, I'll tell you. There are two things like when binary search can be applied. When can we use binary search? When, like, should we apply binary search? This is the question. uh, so mostly, mostly the times when we will be applying binary search is when we want to when we want to maximize the minimum, and when we have to, like, want to have to minimize the maximum. Okay, so there is something that we need to take care about the second half that we are talking to in this maximize the minimum and minimize the maximum. What we have to be careful about when we want to maximize the minimum, if the array is something like we have a mid value, so it's always the binary search will have a mid value, right? Suppose it's 10 and our array has a value like 5, fine, uh, 12, 15, 13, which are greater than 10, 2 and 3, let's suppose. And the operation that we need to do is maximize the minimum. So in this case, if we have 5, then this is fine. Like whatever the question is, the question doesn't matter. We see 12. This individual value is greater than mid. We are saying that okay, my range is 10. I need to keep all the values lesser than 10. But this individual value is greater than 10. Right. That means what we have to take this value, we have to consider this value and jump to the next part. Like we take this value first, and even this is greater than 10, we will be taking this value once and then jump to the next value. We will be taking this value once, we will be taking this value once. So it is something like that. We, even though the value is greater than mid, we are taking the value. And in the opposite, when we are uh, minimizing the maximum. So if the same array is there, if mid value is same as 10, we have 5, 12, 15, 13, 2 and 3. If we have this array, we see that 5 is there, fine, but individually 12 is greater, then we are handling maximum part. We cannot do this. So this mid value is wrong here. We cannot take this mid value. Mid value will be at least minimum of 15. Then only we can take individually each value. So this mid value is wrong here. But in maximizing the minimum, we can take this 12, 15, 13. So this is something binary search twist has. Binary search twist. Try to take this. I'll be back in a minute. I got an order. So just a minute, I'll be back. हेलो. हाँ, एक सेकेंड आ रहा नीचे. I'm back. So you got this intuition what I was saying, trying to say in binary search we need to have this intuition kept in mind, then only we'll be able to like solve the question. So this was like binary search twist. I'd say like split array largest sum. This was like minimize the maximum. So see, if it is lesser than or equals to med, then only we are adding. Else like start from this part and count plus plus. We are moving to the next. Now for in chocolate dot divide, what we are doing is we are adding it, even though it is like possible or not, still we are adding it, and then we are checking if it goes beyond or equals to med. I'll make it 0 again, and parts I'll increase. So it is kind of like similar thing, but the way to present is a bit different. For this it's the same logic, but chocolate divide, this is the like very much same but a little different logic to this. So for the safest part, uh, okay, there is two more algorithm that I should be revising, is union and find and try. Like let's start with union and find, union and find. So I have this let me create a class for this union find class. So we have a union and find class where I will have two things like vector int parent, vector int like kind of rank. These are like private. Now the public methods will be declared here though. So the first method will be like the constructor, where I'll get the size. So I'll resize my like parent dot resize and initialized with like every parent. I'll have to reinitialize it. Okay, and now rank dot resize and everything will be initialized. So initially everyone's rank will be as it is. For int I is equals to 0, I is lesser than n plus I. I'll do what? Parent of I is equals to I. I'll simply update it. Parent of I is equals to I. So this is my union and find constructor. After that I'll have a find method which will eventually return me something. So find parent, kind of find parent, will get a value, or maybe I'll name it as like child. I need to find its parent. Now if parent of child is equals to child, else I'll return parent of child is equals to find parent of child. So this will do my find part, and then we have something as unite. So union, there is a method already there present in C++, so I'm doing underscore union, where we'll get two values x and y. We need to unite them, so I'll do like parent of x is equals to find x, parent of y is equals to find y, and now if it's like it will return whether true or not, true boolean, maybe I'll return boolean. If parent of x is equals to parent of y, will return false, that I was not able to unite them because it was, they were already they were already united. If not, I'll do what, based on rank of parent of x, if it is greater than rank of parent of y, that means x parent is like greater than parent of y. So means so in parent of y will be parent of x will be added, else parent of px is equals to py. One more thing, I'll add it into rank of px plus is equals to rank of py, and similarly rank of py plus is equals to rank of px. So, and at last I will like okay, and last I will return true. So this is my union and find method. Same thing I'll do for try also. We have try, I'll create a try class. Okay, this class will have two things, int is end, So instead of this, I'll create try of children, which will be of size 26, and I will have a constructor where is end will be equals to false. This is not the end, and I'll set this to null. So this is what my try data structure looks like. So there is an insert operation. So we'll get this insert a string, and try root will be with me. So try, I will create a try iterator which will initially point to root, and str dot size plus plus I need this iterator. So if it of I need this character, so let's take this character. So now if it of children of this character minus a, is kind of equal to null. That means this character is not there. So what I will do is it of children, the ch minus a is equals to new try. And after every time it is equals to it of children ch minus a, I'll move to that character, and at last it of is and is equals to set it true. I need to find this specific I'll create a new pointer. Come on. Root. Now I need to check. Str dot character ch is equals to str of I. Now if it of children of the ch minus a, if it is not present, if the character is only not present, then return false. Like else it is equals to it of children of the ch minus a character. And at last I will return it of is end. So this is my insert, this is my find method for try, and this is my try data structure, and same thing with union and find. Perfect. So any more algorithm that I'm kind of missing that I need to like know? Union and find, try. Not sure about it. Let's see. Till now, no. For me, nothing is left. For dynamic programming, let's try for cherry pickup. If this reaches end, return whatever value. If this reaches end, this recursion part is something that I need to know. Like if one is moving one step, the other one can move two steps. So if r plus one is moving one step, the other one is like can do the other two steps. If he's moving these steps, the other one can do like these two steps. So whatever maximum will get, if r1 r2 c1 c2 is like cherries will add once, else cherries will be added up twice, and return memo. Same thing cherry pickup 2 we will be having all the directions. Where is my dirs? It's -1 0 and +1. These three direction k and j. So if one is moving like I will always move I plus 1, and j can move like three direction. He's moving only once and he's moving in three directions. J2 can move three directions. I is always I plus 1. It's always moving once. And if J1, J2 are same, I, J1, else both cherries will be added and returned. And if anyone reaches end, if I reaches end, if J1, J2 is same, return once, else add both of them and return. It's one thing that I need to know, like why. And 2% from the same position to reach the destination. In this case, we can go in three direction: I plus 1 j minus 1, I plus 1 j, and I plus 1 j plus 1. You see that both the robot will go to the next row because they only have j changing, but I is the same for both the robots. Yeah, correct. Every time I plus 1 is, so we can keep only I for both the robots. Correct. Okay, what is this? Let's see. Wall of bricks. Okay, okay. This was the question. Subtracting I minus 1 every time and taking the maximum out of it. So we have this union and find for there. This is find parent, unite parent. Maximum number of edges to remove. Okay, this was like Bob and Alice. So whatever common is there, I will unite in both Alice union find and Bob union find. Whatever whosoever will be having to. And now for 1, if it is 1, I'll unite Alice union parent with Alice, and total required edges is will be plus added with possible edges. It will always be 1 total required edges. Now Bob is connected is equals to 1. Is connected will check what, uh, if its component is equals to 1 or not. We have a component also, and its component is initialized with an. We'll check its component is equals to 1 or not, and Alice component is equal to 1 or not. If it is equals to 1, total edges is this, total edges minus total required edges. Correct. This is one thing that is really good. Alice components, we can keep track of components also. And here maximum safeness factor will create first the maximum safeness factor using Q. and then do a BFS using prior. This is like Dijkstra algorithm where we need to keep track of minimum cost. Why we are minimizing it? So for this, I did it -1, and if it is like 1, I made it 0, and for rest I made it -1. This is something which is rotten tomato, so it will fill up my arrays. Something like this. This is 0, 1, 1, 2, 2, 2, 3, 0, 1, 1, 2, 2, 2, 3, 3, 3, 3. So this is what my array will be filled up. Now I'm starting from like this position. My priority queue is starting from like 0, 0. We have a cost of 3. And this priority queue is keeping the maximum value. Minimize the maximum, kind of. So my priority queue is keeping the maximum, and whatever the cost is new I new j, that cost will be forwarded right from here. If I'm going to here, this is the new like cost for this. From here, if I go to here, still my like minimum path cost will be 2 only, not 3. That's why we are keeping track of the minimum, and my priority queue will keep track of the maximum, and when I reach at the last, will return the cost. Right, correct. This is how we are keeping track of the maximum safeness factor. Okay, so this is also, these 3 questions are done. So mostly our like these revision part is done. Now what I will do is I will pick up these questions from Google and revise all the questions that we have already done. So maybe I'll keep it for full stack and revise everything from start till here, everything, and then we'll remove it, and then we'll revise it again. There are a long list. So let's see. what we can do is like we already know two sum is like the easiest one. I can just skip it. Using a hash map we can create it, we can do it the rest of the part. So if it is possible I'll return it, else I'll push it. So two sum is fine. Minimum number of increments, this question we saw it right now. Merge sorted array is kind of like easy question. We'll start from like 3 pointers, 1 pointer here, 1 pointer here, and 1 pointer here. These 3 pointers will do the job. Whosoever is bigger I'll place it here, and I'll move the pointer, this pointer and this pointer also. Whosoever is bigger I'll add it here and move this pointer as well as this pointer. Now 3 is bigger, I'll push 3 over here and I'll move my this pointer. Now they both are same, anyone can be placed over here, and then I'll move my j here and my I here and k here. Whoso is bigger I'll place 2 here, move my j here, and at last finally we'll be able to have this array. So merge sorted array is like 2 pointer approach. Time complexity will be O of n, like maximum of nums1 or nums2, whatever it is, and the space complexity is O of 1. We are not using any space for this. So kind of I need to revise few of the questions which I've already like written. Range module, shortest palindrome, snapshot array. I'll revise this. Median of the sorted array, median of two sorted array. So these are the questions that are like difficult questions, hard question, but it will get slipped from your mind. Trapping rainwater, lexicographically smallest beautiful string. So this is something like related to linked list. I must say, adding two numbers. We'll add, we'll keep it somewhere, and at last if we see there is still something is remaining, I'll create a new node from there and add it and then return. Let's see the code once. I think this is the only code. Okay, so while L1 and L2 are there, we will do what, we'll add the value, we'll modulo it by 10, means adding the carry also with this. Carry initially 0, modulo it by 10. If result is equals to null, where is the result? This is the first time that we are doing. So result is equals to temp, result will be pointed to temp. IT will also point to temp. So carry will again, new carry will be generated after these, divided by 10, and L1 is equals to L1 ka next, L2 is equals to L2 ka next. So why I'm creating a new I can do it in the same thing. I could have done it in the same thing. I shouldn't have created a new two numbers. Okay, so maybe I'll try to solve this once. Lexicographically smallest beautiful string. So this is something like quite interesting question. We have a b c z, a beautiful string already. I need to create another beautiful string just greater than this. The characters that I can use is all the 26 characters of alphabet. I need to change it and make it another beautiful string if it is possible. If not, then I'll return empty. So checking will be like check whether this new string that we are forming should not contain any type of palindrome. So we already know that there is no palindrome. So skipping the palindromic part will be like checking if the previous element is same as the new element, or the previous element is previous to previous element is also same as this element. If it is, then false, else true. So else true, I'll if it is like true, then I'll replace that character and I'll break this loop. And I'll replace with this character. I'll start from end. Okay, I'm starting from end. I'll go till 0. New character is like from there plus 1 till. So these are the new characters that I can use. So I'll check if I can replace it with this new character. If yes, I'll replace it. And after that I will replace if it is possible to replace it, and after that I'll replace rest of the characters after that to from starting from A. From A plus K, and I'll check it is possible or not. If possible, replace it. Okay, and at last, if everything is possible, I'll return S, else I'll return empty. Correct. This was also a good question. Okay, then we'll go for number of island. These island questions are good. They are like quite often asked in interviews, so I'll try these questions also. And okay, so I'll try it these questions after a short break. Okay, so it's time for a long break. No, I'll take a short break only. When I'll be back, like I want to complete all the questions like till here, at least once today, and then only we'll think of something else. So like possibly I'll take a short break of 10 minutes. I'll be back after 10 minutes, and then we can continue. Okay, so be right back, don't go anywhere. I'll be back soon. Okay, I'm back. Let's go. Mm, let's क्या करते हैं let's solve this question. And let's place it like in the same linked list. Why to use a separate linked list? Like if we are keeping it in the like same linked list, there is one thing that is, if linked list 1 is very small and linked list 2 is very large, what will happen, like eventually linked list 1 will finish and linked list 2 will still be there. So we can connect the linked list 1 with linked list 2, and only one extra like node will be needing in this case, because at last if there is one more carry, we need to handle that part also. Okay, so let's try it. Let's reset the code, and there is a list node it will be like at it. So we'll have while and one more thing, list node root will obviously going to point, and at last will be returning root. Now well, L1 and L2 is there. If both are present, there will be one more thing, that is carry part, carry which is 0. So while L1 L2 is there, we'll do what, and there will be two things like sum and integer like carry. So sum will be L1 of value plus L2 of value plus carry. Which will be nothing but 20. So like if it is 11 or 12, okay, we will be like taking the last digit. I'm sorry, I was confused a little. Okay, I'll take the last digit, and for the same thing, for carry, extra carry, the new carry will be updated to divided by 10. So this will be my new carry, and this sum will be updated in it, which is actually pointing to L1. So it of val will be equals to mm, yeah, even I would say like L1 of val uh, will be updated with this sum value, and we already have carry. So L1 will be equal to L1 of next, and L2 will be equal to L2 of next, right? Okay. So now while L1 is there, means linked list 1 is still there, we'll have to do nothing. I need to have a previous which should be null, and my previous will be updated with whatever we have as L1. So let's handle the L2 part first. Okay, while L2 is there, now if L2 is there, that means uh, I will have to add everything in L2, but my previous of next will be connected with, will now connect to L2 and this will do my job if L2 is there. So while L2, I'll do nothing. I'll do the same thing. This time instead of L1, we don't need L1 here. Simply carry and carry. L2 is equals to L2 of next. We don't want any previous now. Okay, we can keep previous. So previous is equals to L2 while L1 is there. If L1 is there, so everything will be like same except L2, it will be L1 previous. Previous is equals to L1 sorry, L1, and now if carry is there, so what I need to do is like previous of next is equals to new list node. Do we have a constructor? Yes, we have a constructor. Pass this carry there. And at last return the root. So 9 plus 9, it's 18. Okay, 9 plus 9 is 18. So I take 8 and 9 plus 9, 18 plus 1, 19. 9, 1 carry, 9 plus 8, 19. 9 plus 9, 18 plus 1, 19. And L2 finished. So we have 1 as carry. So while if L2 is there, like no, L2 is finished. Okay. We are not updating the value. L1 of val is equals to sum. Here L2 of val is equals to sum. Let's do opposite and see. Okay, so we did it in same L1 only. And perfect. So we only needed one extra node. So even that can be skipped, like yeah, that can also be skipped. I can take this and last node will be connected to this one, which can be done. So no extra node can also be can be used. So lexicographically smallest beautiful string. Let's try this one. So we'll start from like end will be given. So I'll n is lesser than sorry, greater than equals to 0, and it will reduce. Now I need to change this character, right? So what options do we have? We need to like start from here and a plus k. So for char ch is equals to like s of, we have I. I'll start plus 1 and like ch should be lesser than or like equals to a plus k and plus ch will increase. Don't give spaces, that is like Now if I can add this character over here, so if is possible, is like char possible, if is this char possible, so like char possibility will be uh, checked, like this is the character that we want, and this is the position that I need to replace it, right, and this is the string. So if it is possible, like if this character is possible, what I'll do, like I'll replace all the characters from here after this. So like j will start from I plus 1 I plus 1, and j will run till n plus plus j. I'll start from a and char replace character is will start from like a replace ch character should be lesser than like a plus k and plus plus replace character. So I need to check, like can we replace this with the new character, if like is character possible. Replace ch this is the new character, this is the position. Position is not this is the position that I want to replace this character, and s. Okay, if it is possible, replace it like as of I with this ch, replace this character, not at all a problem. If this is possible, as of j is equals to like replace character, and I'll break from here because this is the smallest character that I can replace it with, and if it is possible I'll return s, and at last if it is not possible, like I'll return empty. Let's run it. Okay, sorry, I did not write this method. Bool is character possible. We have character new ch, position I need to check this position and % string. So if like position is greater than 0, and s of position minus 1 is not equals to this new character, like sorry, is if it is equals to new character, I'll say return false. If like position is greater than 1 and then s of position minus 2 is equals to this new character, I'll say like return false, else I'll say return true. What? From where this bracket is coming? We are talking about 4 characters. So okay. Perfect. Oh, okay. I did equals to now. That's why it is creating a problem. I shouldn't be doing this equals to, like, lesser than. Let's go with this. This is a SQL question, which I don't want. So we need to calculate like the number of islands. So we have a position like I'll replace it with 0 and whatever wherever my DFS will take me. I'll replace everything with like 0 and I'll check. Then wherever 1 again, wherever 1 is again. So like simple DFS calls from everywhere. Is there any kind of like follow-up questions to this? An island is a group of ones representing 4. You may assume 4 of an island considered will be same as another if and only one island can be translated. Like if one island can be translated and not rotated or reflected to equal the other, return the number of distinct islands. So they are like same. Um, so they two are not same. If this would have been like And if like they, because they are same. Why they are same? Because like the design is same, so they are counted as one, and they two are like not same, so they are counted as different. Okay. So we kind of have some kind of like dependency. The like shapes can be like kind of similar, but we need to find unique. So how can we think of like finding uniqueness? Like what is something that will tell me if this is one, this is one, this is one, and this is zero somehow. So they are, this is same, and this island is same. So we need to count this and this island, they are like same island, and this island, they are same island. So total number of unique island would be 2 right now. So we need to find unique islands, right? Mm-hmm. Okay, so like we have the coordinates at as like 0 1 2 3 0 1 2 3 4. So the coordinate is like 0 0, we have 0 1 0 0 0 1 and 1 0, and this is the coordinate for this. And what's the coordinate for this? It's like it'll start from I will be here, like I'll start exploring path here. So like my DFS is same, right? So if I explode from here, after this I explode this, so it will be similar. So 2 3, we have 2 3, and then 2 4. After that we will be explode 3 3. So uh, kind of like it's mm, if I somehow know how much far we are, so from here my I is like 2, and my J is like 3. J is like 3. So I maximum I uh, so this is the starting position. If I subtract like 2 3 from all the coordinates, so it will be like 0 comma 0, 2, if I subtract 2, it will be 0 and 1, and if I subtract 2 1 comma 0, So eventually this will boil down to the same coordinate that we have, right? So this is same, this is same, so the coordinates are same. We can say that like they are same. So let's see the same thing for this. uh, we have 0 3. We'll start from like 0 3. So my I is 0, my j is 3, right? Subtract 0 3 from here, so it will be 0 comma 0, and then we go for 0 4. So next coordinate is 0 comma 4. We subtract 0 3 from this, so 0 1. So this is what I'll keep in my map. And this second island which I got is like 3 comma 0. So I have my I as 3 and j as 0. So this is 3 comma 0. I'll subtract 3 comma 0 with this, so 0 comma 0. And the next coordinate that I'll hit is 3 comma 1, 3 comma 1, which is like I'll subtract 3 0 comma 1. So I eventually this coordinate and this coordinate will be boiling down to the same coordinate. And if the coordinates are same, we can like say that they are overlapping. So okay, so this can be stored in some kind of set of vector of integer, right? And whatever the size of island like set would be, I'll return that. Whatever the size of set will be, I'll simply return. So that will like eventually give me the optimal coordinate, the optimal answer that we want. I like unique, because we need to work on the like coordinates. We cannot skip the coordinate part. Is there any other way to optimize the space that we are taking? So the time complexity will be like O of n only, O of n only, and like n cross m, whatever 2D grid will have, the like time complexity will be big of n cross m. The space complexity for this will like change. It will also be big of n cross m, because the maximum that I can store is a whole grid into a set. But every time say this set is like being sorted, so kind of log n time more is what we will be having. So log of n cross log of n cross m, n cross m into log of n cross m. So this will be like the time complexity for this. Space complexity will be O of n cross m. Can we further optimize it? We can like make a string type unordered set of string type, and like we can keep the coordinates in a string format, and then we can do it. That can also be done. Hmm. So if I use unordered map and as a string, I might reduce the complexity. So it's the maximum length, it's 50 cross 50 at 10 to the power 2. So it's possible. I'm like, can be done. Whatever I'm thinking is possible for this. So this Roman to integer is something not very much tricky, but it's kind of conversion is I'll keep a set here. Whenever I'll get a value which is greater than the top value on the set, I'll try to reduce it uh, until unless we find a value. So that is what I will be having. I'll keep a set. Whenever my stack top value is lesser than the value that we got from here, I'll subtract it from my value, I'll pop it, and at last I'll push the value, and at last will like empty our stack and add it everything to my string resultant, and I'll return the result. So this is a follow up. This has a follow up. Could you do it in one pass? Yes. So we have a difference. Like from last, I need to like remove the two second element, second last element. So for this, what I can do, like I'll start a start pointer, and uh, I'll move it until and unless we find a value which is mm, which has a difference of 2. So whenever we'll cross two nodes, I'll start a previous pointer kept here. So these two will move forward. So whenever my current pointer reaches here, my now the previous pointer will start from here because the difference is 2. So I need to have two nodes in the back. Now my current pointer will move here, my like previous pointer will move here. Again my current pointer will move here, my previous pointer will move here. Now current next is null. What I'll say, stop here. I don't want to move any further. I'll tell that previous whatever excuse me. So I'll remove this next node. So this will be connected with current. If n would have been 1, then it would have reached here. If n would have been like 0, nothing would be. So this is the one pass solution for this. Okay, trapping rainwater. This is something I need to find the highest tower. So that will be done by O of n operation and a single variable. I found a highest tower index. Then I'll start from start till I reach this highest tower. I'll check the highest tower and this minimum. So this is 1, like this is 0. What is the lowest value from back? No, what's the highest value from back? We'll move like that, and then we'll check the minimum, and then we'll start from back. Same thing, highest value, and whosoever is the minimum, I'll into this water value. So this can be like done in O of n operation without taking any extra space. So O of 1 is the space complexity for this, and O of n is the time complexity. So it'll be kind of two pass solution. Else we can like have a right maximum, which I'll keep, and then we'll we'll add water to it. Simply subtracting. Yes. And left max will keep track of the maximum value from left. Okay. So we are given an array. Group the anagrams together. This is something like unordered map, keeping sorted, and then pushing back all the elements. Sorted, push back, and add it in the result. So this group anagram is also like fine until unless we have some kind of sorting. This is the only way. Maximum sum subarray. So whenever I'll reach a negative value, I'll check If nums of I is greater than like previous maximum, and so I'll take the nums of I or the previous maximum, and G max is equals to current max plus G max, which I'll be doing. So this maximum subarism is also fine. See, merge intervals, I've solved it many times, so I think I will be able to solve it. Okay. Ah, if an element is 0, set its entire row and column to zeros. You must do it in place. So if the element is 0, I'm setting this row and this column to 0 0. In the first iteration, wherever I see that top row and left, set it to 0, and in the second iteration, like wherever I get a 0, like start from here and here. So if in this row, if I get a 0, whole column will be 0. If this we get a 0, whole row will be set to 0. That is what in place logic is. So I'll iterate over it. If we found a 0, now what I'm doing is I'm setting it to integer max. Okay. Okay, I'm changing it to some other variable. Okay, that is also like possible, but I don't know. I've solved this question. So wherever I get 0, change it like, and wherever I get this integer max -1 value, I'll make it like 0, of course, and rest of the things are 0 already. So that's in place only. Okay, we have LRU cache. So this question I solved it recently, October 26th. So this was like a good question. Left dummy, right dummy. It's a good question to like solve if you are doing LRU cache. So try this question. This is like really good. I created these two new methods of removing a node and adding to right of the node. I would recommend to like try this question. This is a good question. LRU cache. Okay, so we are till here. We need to go like 1 2 3 4 5 6 7 8 9 10 11 12 questions more. Okay, let's take a 10 minutes of break and then we can go. So I think there are like few questions which are hard. This range module, I'll try to do it again. Vertical order traversal, I did it recently. Earliest moment is like a union and find question. The height of a binary tree after subtree removal, I also solved it recently, so like it's fine, but I'll at least I'll go through the logics, sliding window maximum also, and few extra questions that I have is like median of two sorted arrays, snapshot array, all over one data structure. I'll try those also. So yeah, these. Let's go for a 10 minute of break, and after that we'll try to cover up as much questions as we can from count primes. So we'll see you in 10 minutes. Don't go anywhere. Okay, I am back. Woohoo! Let's go. Hmm. So we have count primes, handling window maximum, meeting rooms 2, subarasum, permutation. So count primes. There are 4 prime number less than 10. There they are 2, 3, 5, and 7. So like n can go 5 into 10 to the power 6, and I need to count prime for each and every value. So it's like there was a sieve of Eratosthenes, something like that. There was some logic uh, that we can use. Else, I can use like start from every number, go to its square root, and check like if any of the numbers is divisible or not. So like do a iteration, start like this is one I was doing like I started with 4, like j is equals to 0 till I have array of like square root of I if like any of the values divisible by, so set flag 1 and break from there. Like it's not possible. Okay, if flag is 0, then is it even like reducing the time complexity? And like if yes, then how? From 4 I'll start from 4 till n. uh, hmm this is something that I need to know. Easy sieve of Eratosthenes. Yeah, I know that it's like like he's saying 2, 3, 5 and 7. Not solving this one, but the classic solution is known as sieve of error Eratosthenes. For the sieve of Eratosthenes, we start by creating a Boolean array scene of size n to represent each of the numbers lesser than n. We start at 2, and for each number processed, we iterate through and mark each multiple of num, starting with num square as seen. Since there are also a multiple of the similar number, for example, when processing fives, we can skip to 25 because 10 will have been seen when we processed 2, 15 when we processed 3, and 20 when we processed 2. Then we move num forward, skipping any numbers that have already been seen. By doing this, we'll only stop on prime numbers because they haven't been seen as a multiple of previous iteration. We just have to update the count answer each time we stop, and then return answer once we reach n. So it's we have everything as false, answer is 0. Start from 2 till n. If I've seen this number continue, if not seen, then answer plus plus, and so multiply num into num, start from 4, and in multiply reaches n, multiply plus equals to num, and seen make it true. Now 3 I haven't seen, so I'll start with 3, 9. 3 as I've seen 3, answer plus plus, and 9 all the iteration until and unless we reach same as 4. We will be seeing, we have seen 4, we saw 5, no we didn't saw 5, so 25. So n log n log of log n is standard, but some article will say with below optimization, that is I is equal to time. So So like kind of I need to remember this sieve of Eratosthenes, which could eventually like help me find the answer. Where is this ARR? Oh, there it is. When did I solve this? On 2021. That's why. Okay. Let's solve this again. Using like sieve of era, SIEVE, sieve of era Anyways. Okay, so we'll have a vector of kind of bool that we see in this number or not, everything initialized with false. So like the prime numbers always starts from 2, so I'll start from 2. Int I is equals to 2 will go till n plus I. Now if I've seen this, if scene of I is equals to true, I'll simply continue to the next number, else I'll add it in my total prime, and I'll start from, it's like I'll mark everything as seen of multiple of this. So mark which will start from I into I mark should be lesser than n, mark plus is equals to this I. And then like scene of this mark is equals to true, and at last I'll return like total prime that we have. Okay, sorry. I need to have a long here. Okay, make this also long. N was something like this, so let's take one more n, which is 5 2 3 4 5 6 into 10 to the power 6. So okay, the sieve of Eratosthenes, whatever it is, I'll just try. I need this. This is a like nice thing to know. mark this solution over here. Submit it again so that it should be kept in history. Fine. Sliding window maximum. Okay, give me a minute. I'll be back in a minute. I am here. Okay. So we are given an array of integer norms. There is a sliding window of size k, and I did a submit it 2023, which is moving from like the very left to of the array to the very right. There is a sliding window of size k, which is moving from very left of the array to the very right. You can only see k numbers in the window. Each time the sliding window moves right by one piece, return the maximum sliding window. So we have 131. Okay, so every time I need to like keep the maximum, I need to return the maximum value. So maybe I'll keep the maximum value at the top always. So if 1 comes, 1 will be there. If 3 comes, I'll check 3 is greater than 1. Yes, so I'll remove 1, I'll add 3. I'll try to keep the maximum value at the top. So if 1 is there, if 3 comes, I'll move this out 3, and I'll move this one, and I'll put this 3 here. Now negative 1 comes, I'll add this negative 1 over here. Now this window has a maximum value of 3, so 3 is like first time. Every window I have 3, I pushed 3. Next I'm removing this one, like the value at index 0. If I add negative 3 to it, negative 3 is still smaller, so we added 3. So kind of if I find a value, like I want to remove like okay, so it's a 0 1 index is 0 1 1 is like, so 0 will be popped and 1 is pushed. It's like 1 3 negative 1 negative 3 5 3 6 7. We have 0 1 2 3 4 5 6 7. So 1 3 was greater than, so this index was pushed. Now at 2 we have negative 1, so the 2 index is switched. Now these values inside 3 window is done. Now I go to the next window. So if 3 is if 3 index value is 3 index is there, value is negative 3, so negative 1, the value is smaller, so 3 index will be like here. We have dealt with this, so like 1th index value is 3, still 3 is dominating. Next comes 4 5 we have, so everything will be popped and 4th index will be pushed, and we have 5 over here. This 3, so we will be pushing 5th index over here. We have 6 with at 5 we had like at 5 we had 3 removed, have this removed, 6 is pushed again. At 7 so this will be popped and 7th index will be pushed. Now there is one thing that What if my window size is 3 and we have 3 2 1 0 0 1 2 3? So 3 is like a zeroth index. We have zeroth index here. 2. Second index here. Now 3 value is complete. I have this 3 whose value is 0. So like the size is full. And the next value that should be included is like, so front will be removed. This is what will happen, right? So if let it be like while dq is not empty and nums of dq dot back is like lesser than nums of I, I'll pop it until and until my dq becomes empty. I'll push it in my dq, this current index, and if I goes is like greater than k minus 1, I'll push the dq dot front value whatever we have in the dq dot front. There's only one thing. If dq dot front value is lesser than what we have current minus I minus k, so I'll remove it from front. Because the only way it will fill all the my priority queue will be filled is like dq will be filled up when we have the value in descending order. Then the starting value will always be the one which will be popped from front. So if I minus k, if it is equals to I minus k, which is like 3 minus 3 0, I'll pop the front value. This is what the sliding window maximum says. So I'll have a dq I'll have this result. Let's start with so if not dq dot empty, if dq is not empty and the dq dot front index is like smaller than or is like equals to what current index minus k is, then I'll do dq dot pop front. Now while not dq dot empty and dq dot uh, like nums of dq dot back, the value is like smaller than current value nums of I. So I'll keep on popping from back, and then I'll simply push dq dot push front this. No, why I'm pushing it front, push back. If I is greater than I equals to k minus 1, so result dot push back dq dot front. And I need to push the index, and at last I'll return my result. Ow, ouch. QUEU. Hey, what is the spelling of DQ, man? Acha. D, acha, okay. DEQUE. Oh my god, DEQUE. So this was sliding window maximum. Okay. Let's go to the next question, which is meeting rooms 2. It's like based on priority queue. So this I have solved recently, October 16th. Oh, it's on my birthday. Great. Given an array of integer nums and integer k, return the total number of subarrays whose sum equals to k. So it's kind of okay. What is something that will fail? I agree to this solution. I totally agree to this solution that if there is a sum that is also, that will be like, it's because uh, it's there we are here we are including negative numbers. If negative numbers were not included, negative numbers will create a problem. Because if suppose my like k is 3, I have this as an example, negative 1 and 3. So I have this negative 1. After adding to this, it will be 2. I still haven't reached, but 2 minus k, that is negative 1. Did we saw negative 1 previously? Yes, we did saw negative 1 previously. So that means from here to here we have a value as 3, correct? Because we have negative solution. It's kind of a prism that we are doing over here. So if prism, sorry, dot find this sum minus k, if it is present, so like we'll add in my prism as 0 is equals to 1, and it is not equals to prism dot end. What I will do is like total count of plus is equals to pre sum of sum minus k, and pre sum of this sum will be increased. I'll return total count. So we have this character, so until and unless this character uh, so we have this in like v1, and we created a v2. So we added this character of string 2, and it went like beyond this character. So until and unless it is like greater than this same character, I'll be subtracting and my left will be increasing. If my right minus left plus 1 is equals to s1 dot size, return true. Yes, so this is fine. So now we need maximum swap, maximum area of island. Here comes the range module. This is just a simple what do I say, a DFS solution where I will be counting whatever nodes will be getting. So it's fine, this can be done. Now this is the like a good question, range model. I'll start this after this break. So we have this kth largest element. So we have 4582. So I need to find the third largest element. I need to keep track of the third largest, which I will keep in priority queue. Whenever a value comes, I'll check in my priority queue if that value. I'll keep the priority queue as the lowest on the top. I'll move for this 5 for 10. Still 5 for 9. This is like a priority queue thing. I'm not sure if I solved it using priority queue or not. Yes, I did. I recently solved it. No? Okay. Oh, I skipped this maximum swap. You're given an integer now. You can swap 2 digit at most once to get the maximum valued number. Return the maximum valued number you can get. Okay. I'll check with 2 if I get any number which is like possibly the highest number, and if it is greater than 2, I'll swap that number with this. If not, then I'll start with 7 and I'll check. So number will be like very small. So while j is greater than I, I started from zero. Like obviously I'll start from left. J okay, from back I'm starting. If in str of j is greater than the I index, and if index is negative 1, then this. If else, I'll also check with the str of index and update the index, and j is subtracted. So if index is not equals to negative 1, that means I'll swap and break, and so like I converted it into string, and then checked it. Okay. And if it was a string already, and the size would have been like humongous, so I can keep something, some pre-calculation thing, like what is the maximum value. If there is some value, some index which has a maximum value than this, I'll just simply swap it. So that's a pre-calculation that we can do. For this range module, okay, now we are left with 4 more question. Range module, vertical order, earliest moment, and height of a binary tree. Fine. So we'll take a break, short break. After this we'll start, and then we have for 3 months we have few more questions. I remember this majority element, intersection of two arrays, median of two sorted arrays. So there are lots of questions that I need to solve. Spiral matrix, decode. Okay, fine. I'll take a 10 minutes of break, and then I'll be back. We'll be going with the last 4 questions, 1 2 3 and 4 range module. I'll start from range module, then vertical order, traversal. We'll discuss this because I've already solved it. Earliest moment, we'll discuss this also, and we'll discuss this also, but I'll solve this. Okay, I'll be back after 4 minutes of break, 10 minutes of break. Don't go anywhere. Okay, I'm back. Let's go with the range module question. So in range module, what we generally do is we do not keep the range overlapping ranges in the map. So we'll always like remove the overlapping ranges from the map. So like we have a map of integer comma integer. Let's say this as range. Now we need to like add range in this. So whenever we are like adding a range to it, we will check. We'll start like iterator. Auto it is equals to like range dot upper bound of left. Now while it is not equals to range dot end and end, I need to check like whether my right is greater than my first value. Is like if it is greater, I'll try to no, if whether my my left whether it is overlapping case or not. So if it is overlapping, my right would be like obviously going to be greater than this its left. So if my like right is like greater than or like even equals to not greater than my it of first, I would say like if it of first is lesser than my right, I would eventually like means increase, but my right will be updated with maximum of whatever we have in the right or it second, and then I'll increase it and I need to erase from range dot erase previous of it. So this will like do. There is one thing that I'm skipping is I found a upper bound of left, so there might be a possibility that my like left value, this left value is going lesser than like. So if it is not equals to left dot begin, if it is not equals to left dot sorry, not left dot begin, sorry, range is not equals to range dot begin. If I If this is not the starting, I am skipping a value. So and mm, previous of IT second is like greater than my left. That means left is like colliding with this. So what we will say is, okay, I'll update my right as maximum of right, or previous of I'd simply like go IT minus minus, and I'll check IT of second. So if it is overlapping, that means there is a then I can directly like update the IT of second with maximum of right and IT of second. Else if it is not, then I'll add range of left equals to right. That is simply I'd say add range. We have like removing this range, so it will work very similar to what we have. But here one thing that I need to keep in mind is like a cut end. Like I'll have to have a it will be same thing. Auto IT is equals to range dot upper bound of left. I'll have a cut, and that is initially -1. Now while it is not equals to range dot end and again like my right is like is going beyond its left. So if right is greater than, or I would say, let's if IT of first is like lesser than my right, so like cut end would be maximum of cut end or IT of second. It's not current end, it's cut end. And IT plus plus and range dot erase previous of IT. Now there is one more cut that we need to check. Now if IT is not equals to range dot begin and my IT of second is like greater than my left. That means my left is lesser than IT of second. So there's something I'm cutting over there. So I'm cutting this half so I can directly like update my IT of so maximum of cut end or IT of a second, and I'll do what. Okay, this is, we are talking about previous of IT. It's like IT minus minus. I checked my maximum cut end, and if this is the case, IT second would be updated with like from here till here. Now there is something that I need to check. If my cut end is greater than my right, that means some portion is left. So what I will do is I'll add in my range from right till and for like query range, so I'll be doing IT is equals to range dot begin and no, sorry, range dot upper bound of left. Now if IT is equals to range dot begin, I'll be returning false, else I'll return previous of IT. Second, if it is greater than or equals to, if it is greater than my right, even if it is equals to, what does that mean? Do I need equals to here? Right. It's something very small that I'm maybe kind of equals to, if we add equals to here is if it of first is like lesser than, do I need equals to here? Yes, we are talking equals to every time. Okay, so we are good with this like range module. Let me like think over it why we did equals to, like if it of first is like smaller than or even equals to my right, um, I'm, I'm, I'm saying that merge it. Because left is somewhat included. Left is like, this is first part is like inclusive part. This is a big bracket, so it's inclusive. That's why we are like taking it as inclusive and not exclusive, right? And same thing, we are talking about left, so it should be like left is always inclusive and right is exclusive. So wherever we are talking about like first part, this first is always the left, and here we have left. Here might be like we are talking about second, uh, like if previous of it of second is greater than my right. What if like if I do greater than or equals to right? So obviously like this is not inclusive part there, that's why. Okay, so every time we are dealing with left or thing, we are dealing with like equals to and all. Like this is one of the insane question, I would say, like which taught me a lot of things. I would recommend you, if you are seeing watching this, I would recommend you to like try to solve this range module question. It's very intuitive, and like you'll get to learn a lot of things from this question. So range module is done. Vertical order traversal and earliest moment and height of a boundary. So vertical order traversal is like very much two things we need to track, like the vertical level and the horizontal level at the same time, and we need to keep it somewhere, and I need to sort it, and I need to insert it. So this is what we need to like do for the vertical order traversal of a binary tree. So I don't think that this will I solved this question very recently, October 29th and 3rd November. So it's like I solved it by my own, so I know how I'm doing it. So if you want, you can try this question, and if you are having any doubt, do let me know. I'll help you, and I'll guide you in this question. So this is not the hardest question, I would say. Okay, the next question is the earliest moment when everybody became friends. So this is something related to union and find, where at a time we are uniting them, and we see if there is only one component at the end. This is okay, I kept it at the last, why I don't know. Okay, and I'll check if I have only one count, then I'll return that. Like one count means if I have only one parent uh, for all the friends, then that means like everyone has become friend. So that is the time where we need to return. So this log, if it is not coming in sorted order, we might need to sort it. Okay, there is find parent, make union. So make union. Why we have this find and union again? Come on. Twice, same thing twice. Why? If it is sorted, no, we need to sort it. And if there is no time where anyone became friend, we'll return like -1. So answer is simply -1, nothing else. So I can remove this answer from here, direct return -1. So this is something from union and find. So you'll be able to solve this question very easily. If you know union and find logic, I think you won't be able to like have difficulties in solving this question. Okay, this is a height of a binary tree after subtree removal queries. This is something related to like pre-order and post-order. I'll try to explain it if possible. Let me see. I have this one. I'll start with this one, like pre-order traversal will tell me maximum height from left, post-order traversal will tell me maximum height from right. So pre-order ORDR traversal. So we have this pre-order traversal 0 1 2 will fall back 2. Currently 2 is the maximum from left that we have got. let's try this example. So this is a little bit better. Okay, currently my height is 0, then 1, then 2, and then 3. For this also it will be 3. For this also the maximum height from left that is coming is 3. For this also 3, for this also 3, for this also 3. This is for pre-order traversal. Now if we do the post-order traversal, what we will be having, let's draw it. So we have 5, we have 8, we have 9, we have 3, we have 7, we have 2, we have 1, we have 4, we have 6. Okay, so the post order traversal will go from right, so 0, 1, 2, for this also 2, for this also 2, for 2, for this also 2. This will be updated with like 3. So for this, if I remove this, what is the height? We'll have as 3. So for this it'll be 3 what we are checking from right. So this is like the post order traversal, and wherever we'll remove the queries, like if we are removing 3, so from 3, if I'm removing, so 3 will say what is the post order from right, so 2, and from left it is 3, so maximum is 3, will be returning 3. Similarly for 2 also, we'll have, if I remove this whole 2, post order traversal will tell me that it's 2, and pre-order traversal will also tell me it's 2, so 2 is the height. If I remove 4, what if we remove 4? So if we remove this 4, my post order will tell me that it's 3, my pre-order will tell me also it's 3, so it's 3. Now for 8, if I remove 8, where is it? My post order tell me that it's 2, and my pre-order will tell me it's 1, so whichever is maximum I'll return this. So this is what we will be doing, how we will be handling using pre-order and post order traversal. So we are always like starting from max height as 0, and keeping post in a map, we are keeping post height and pre height to this, and maximum height and current height. Backside we are having this as global. We could have passed it here also. And after that it's very simple, just to find the maximum and push back and return the result. Okay, seems like we are very much done with this part. 30 days, maybe I'll try, we still have 20 minutes, so I'll try some question from last 3 months. This done. We have done this. Container with most water, done. It's like 2-pointer approach. Longest consecutive sequence, longest common prefix, largest rectangle in histogram, grouping anagram done, climbing stairs, It's the Fibonacci series, majority element, shortest palindrome. Let's see. Median of two sorted arrays. Okay, this is a interesting question, I would say. So if there is a 99%, I would like skip it. For is 3 present, yes, skip it. 200. If is 0 present, no. So I'll start from 0 1 and I'll find 2 3 4 every number and max streak. This is like a good question, I would say. Try this question, longest consecutive sequence. This is O of n solution, what I'm telling you. So if you will not able to find it, let me know, I'll explain you. Longest common prefix, it's the try solution. Everything I'll try it, and is end. Okay. Okay, I sorted it, but uh, I I could have reduced the time complexity without even sorting it. We could have kept a like counter variable which will initialize everything. So we need to know like what's the size till there. That would have told me like possible or not. So the sort is something, let's say, taking a lot of time complexity and log n, and I don't want this. So that this can be like reduced. Okay, I need 2 minutes. I think cook is here, so I'll be back in 2 minutes and then we'll start again. Just give me 2 minutes. I am back. Okay, where were we? Longest common prefix. It's like a try solution would have been improvised on it instead of sorting. Okay, next is the largest rectangle in histogram. uh, this is like left fill, right fill max. I need to left fill max. So if height of st of top is like greater than or equals to, uh, till that I'll be popping. If stack becomes empty, else st of top minus 1, and left max, for left max top plus 1, for right max minus 1, and then we'll calculate. So this is like a good question, but like I've already solved it, so I know how we will be solving it. So this is like Boyer Moore voting algorithm where I'll start voting. So we'll have this vote and val. If vote is 0, I'll take this value in my val, and if the numbers are same, I'll increase my vote, else my vote will decrease. So if it is 0, I'll take this number, and at last I'll return simply val. So this is the majority element, shortest palindrome. So I can you can convert S to a palindrome by adding characters in front of it. Return the shortest palindrome we can find by performing the transition. So finding the shortest palindrome is like reversing a character and comparing it. So whatever the maximum value that we'll get at the end, simply doing the KMP algorithm will do the job. I have this previous this KMP filling. It's the needle part that I would say is what it is. Let me change the logic here. So now if new str of I is equals to new str of j, if they both are equal, I would say like just increase I and j both. If they are not equal, then I need to check if j is equals to 0. Just simply increase I, else let I be there and increase j to like KMP of j minus 1. While I is lesser than new str r dot size. Ouch. I haven't added it in my KMP. So KMP of I will be like j plus 1. Else I can do KMP of of I as 0, it doesn't matter here. Even if I like remove this, it will not affect our solution, correct? Okay, so this is like a good question, median of two sorted arrays. Okay, if I'm trying to keep like nums1 as smaller and nums2 as bigger. So nums1 dot size is greater than nums2 dot size, then like swap the values. M is equal to nums1 dot size, n is equal to nums2 dot size, and low and high. Now cut it from here. If I divide my low and high, this is my cut 1. What will be my like cut 2? M plus n plus 1. Why we are adding plus 1 here is because handling the even and the odd part. Divided by 2 minus cut 1 will tell me like how many we need to need on the left part. To divide it into equal half. So we'll have like 4. So left 1, left 2, right 1, right 2. Left 1 is equals to, if cut 1 is equals to 0, if I'm at the like starting position, I would say int min, else nums1 is equals to cut 1 minus 1. Left 2, if cut 2 is like 0, then int min, else nums2 of cut 2 minus 2. And right is, if cut 1 is like end, then int max. So I'll try to make left hand side values lesser. Cross values should be less. If the cross values are less, if left 1 is lesser than equals to right 2, left 2 is lesser than equals to right 1, if this is the case, I need to check. If it is even, then I need to return maximum of left 1 or left 2. Else maximum and minimum plus 2 divided by 2.2. Like if it is not even, if it is odd, I'll return the maximum from left and right, left 1 and left 2. If it is like even number, what we'll be doing is we'll be returning maximum of left 1, left 2 plus minimum of right 1, right 2 divided by 2. So based on this, if left 1 is like greater than right 2, I need to change my pointer, swap my pointer. So what will be like my mid, what will be my low and high pointer will look like. If my left 1 is greater, I need to make it smaller, correct? So my high will like reduce to cut 1 minus 1, and this is the like actual mid we are talking about. How many more we need on the left part to divide it into equal half. So cut 1 minus 1, else low is equals to cut 1 plus 1. And if nothing is possible, like return 1.0. So this is the median of two sorted array. Okay. threesome, remove element, spiral, decode range module is done. Longest substring without repeating character is like simple reverse integer. What is this? Let's see. Valid parenthesis, remove duplicates from sorted array, combination sum. Let's see this one also. Jump game, merge interval, square root, set matrix 0, word break. So evaluate reverse polish notion. Largest number. This is a binary search. So I need to be careful about the negative numbers, right? While x is not equals to 0, I'll start. What we have here, remainder, adding a reverse this, and x is divided. What's this that we are talking about? Okay, like if reversing a number goes beyond my integer max. Okay, so if reverse a number into 10, so we are taking it as a double. If not, we can take it as a like integer. Let's see if it is possible, because we need to like reverse it. Yes, assume the environment does not allow you to store 64-bit integers, signed or unsigned. So it's we cannot adjust a 64-bit integer, and we are like taking double, so it's not possible. So I'll need to handle it within this only. So what's the largest value integer max can attain? Int max is like this. This is the largest value that it can attain, which is like int max is equals to this, and minimum, what is the like minimum value int is this. Int minimum is this, right? we need to like check if we are reversing a number, it should not go beyond this, right? Okay, so we need to like mm, check if the number of digits that we reversed till now is 1 2 3 4 5 6 7 8 9. If we have already reversed 9 digits, now 10th digit is what the starting digit that will be placed at the end. So the last digit should not be greater than 7. This is what I'm supposing. So uh, if I see if integer max, if I divide it by 10, correct? And if the number that we have till now is greater than this number, and the last digit is greater than 7, uh, then we would say that it's not possible. But okay, divide by 7 will get the rest of the numbers. What, like 6 5, but the last digit is like lesser than, so 647. I cannot go 6 5, even if last number is like 61. So divided by 10, if the current number is greater than this, uh, I would say, and if not greater than this, if it is like even equals to this, so the last digit should not be greater than 7. And if the number is greater than this, whatever value we'll have in the last doesn't matter, it will exceed my integer max, right? So like if my reverse digit is greater than my int teacher max divided by like 10, uh, if it is greater than, if I remove the last digit, if it is greater than, then we'll return, or the number reversed is like equals to int max by 10. Even if it is equals to this and the remainder that we are talking about, and the remainder, last digit is like greater than 7. If this is the case, like I'll return 0. Now if it is negative, now if reverse of number is like lesser than int min divided by 10, or kind of reverse till now is equal to int minimum by 10, and the remainder that we are talking about is greater than 8, then I would like return 0. Else I'll do it. Okay. Okay. Let's take this. So, okay. Runtime error, use test case. Let's use this test case. Perfect. Ouch. So this was the like actual logic. For reverse an integer. Now reverse is also integer, so everything is integer within range. Perfect. This is a DP question, a simple DP cursive plus pick not pick part. Sorry. This is where my merge sort. Arrange them such that they form the largest number and return it. So the return type should be in string. Okay, here comes my merge sort. So what I'll do is I'll have string, I convert it into string to string, and I pushed it in nums of string. I started with merge sort. Merge sort is the logic is like s1 plus s2 is greater than s2 plus s1. Then return true, else return false. So this is my merge sort. If left goes beyond my right, I'll return like str of left. Anything mid, I found mid, stopping the overflow. Here this is my left half, this is my right half. So left mid str, mid plus 1 right str, and merge left half and right half. So while merging, I'll start a sorted string which will be returned at last. sorted string. I'll check this plus this is greater, or this plus this is greater. So which one should I go for, 3430 or 3034? So we'll start from compare. If it comes out to be true, I'll add my left plus plus. If comes out to be false, I'll add my right plus plus. While left is there, while right is there. This is the comparator where we need to remember this. Compare strings s1 plus s2, s2 plus s1. Whosoever is watching my stream, can you comment in the chat? Let me know who is watching my stream. So this is very much based on the merge sort. Worth a read. A and B are numbers in string format. So this is a n log n approach. Longest common prefix done. This is n log n. It has a n log n approach. I think it's like binary search, where we have pushed 0. Now if num of I is greater than the last value, I'll directly push it. Else I'll find its best place to be pushed. Find mid. If nums of I is lesser than is lesser than this result of med. So I'll move my right pointer to mid -1. I'll shift left because the value is smaller. Else I'll move to right, and I'll place it my result of left to nums of I directly. And lastly, the result of size will tell me what is the longest increasing subsequence. Okay. There is one Russian doll envelopes. Let's see this one also. So there was one thing I need to sort. If a1 is greater than b1, I sorted it on the basis of start comparator. So if a0 is smaller than b0, if a0 and b0 are same, try to keep the larger one at start, and then we don't care about the start, we only care about the end. So it'll take the same logic, increasing subsequence, everything would be same. We are only handling the right part and not the left part. Is there any other solution than this? Okay, there is something. S1 plus S2 is equals to S2 plus S1. If they both are same, like S1 plus S2 and S2 plus S1 is same, then compare S1 of substring, then return S1 of substring from 0 to GCD of size of S1, size of S2, else return empty. He went God mode over this. Akshay Kumar 2 star. हाँ जी पूरी मन तो नहीं है दीदी हाँ ले सकते हो आप देख लो आप ख़राब तो नहीं हुआ ना हाँ तो फिर ले लो हाँ खीर खा लो ठीक है दीदी थैंक यू saying like this plus this and this plus this are equal, then find the GCD of these two and start from 0 and size of this GCD. That will be returned, else return empty. So ABC ABC plus ABC ABC or ABC ABC ABC, if they both are same तो 6 और 3 GCD आएगा 3. Amazing solution. I'll like mark this. What is this? JavaScript? TypeScript, JavaScript. No, I don't want this. Okay, I think I'll stop here for today. And it's already 8 hours I've streamed, so I'll stop today here. Hopefully tomorrow is like my office, so probably I'll not be able to stream this week, so I'll be streaming Saturday. I'll be back again, we'll start streaming. So like, thank you everyone who have joined and watched my stream. Thank you very much. I hope you liked it. We did a lots of question today. I would say like we revised every algorithm today, and also we learned new Bellman-Ford algorithm for detecting cycle. So we revised lots of things today related to graph, dynamic programming, and everything. And we solved too many questions also. Even though I've solved them, but I did revised everything. So yeah, thank you everyone for watching this stream. I hope uh, we'll meet next Saturday again live. So see you next Saturday. Have a great day. Bye bye.